Okay, let's dive into this. Welcome to today's explainer on physical science. Today, we are going to look closely at atoms, molecules, and the conservation of matter. I actually want you to think of this explainer as a sort of microscopic detective story. We're going to solve the ultimate mystery of where matter actually goes when it seems to just vanish right before our eyes. I mean, we see things change form, burn up, or dissolve every single day, right? Well, it's our job today to track down the evidence. So here is the roadmap for our investigation. We'll start with step 1, the invisible building blocks. Then we'll check out models of matter, crack the conservation rule, look at reactions in action, and finish up with your engineering challenge. Let's get started. Section 1, the invisible building blocks, zooming into reality. It's time to shrink way down to the microscopic scale to understand exactly what makes up the everyday things we can touch, feel, and see all around us. Seriously, I want you to look around the room for a second. Look at your desk, your computer screen, maybe a glass of water nearby, or even just look at your own hands. What makes up everything you see and feel? If you took a piece of paper and kept tearing it in half over and over again, way past the point where you could even see it with a powerful microscope, what are those fundamental, invisible pieces of the universe actually made of? The answer, of course, is atoms and molecules. They're the fundamental particles that combine in all sorts of various ways to make up absolutely all substances. Now, for our grade 7 learners diving into this, let me reassure you right now, we are just focusing on these basic building blocks today. You don't need to worry about the complex math of bonding rules, valence electrons, or atomic masses just yet. For right now, we just need to understand that atoms are essentially like the individual Lego bricks of the universe. And molecules? Well, they're the structures you build when you snap 2 or more of those atomic bricks together. Moving on to Section 2, Models of Matter, Visualizing the Invisible. Now, what's really interesting about this slide is the incredible contrast in how atoms actually arrange themselves. On one side, we have simple molecules. Think of things like ammonia or methanol. These are just small, tight-knit groups of a few atoms bonded together, basically moving around as independent little units. But on the flip side, we have extended structures. Think of sodium chloride, which is really just regular table salt, or a diamond. These aren't just tiny independent clusters, they are massive, repeating, three-dimensional grids of atoms all locked together. It is literally the difference between building a single tiny Lego spaceship and a giant solid repeating wall of bricks. Because atoms are, way too small to see, we have to talk about how scientists actually study these invisible pieces. Basically, we rely on physical or computer-drawn models. Scientists use 3D ball and stick models, digital representations, and really detailed drawings to picture different types of atoms and how they link together. These models are absolutely essential tools. By visualizing the invisible, we can start to predict exactly how a gas like carbon dioxide will behave entirely differently than a solid, extended structure like a diamond. Section 3, the conservation rule. The great disappearing act? This brings us to the central mystery of our lesson. What actually happens to these atoms when matter seems to disappear entirely or change into something completely different? So the crucial point is this. The total number of each type of atom is conserved, and thus the mass does not change. This is known as the law of conservation of matter. It essentially means there's no magic in the universe. Matter is never, ever created out of nowhere, and it is never destroyed. If a puddle of water dries up or a piece of wood burns down to ash, those atoms didn't just cease to exist. They simply regrouped and floated away into the air as different molecules. The mass stays exactly the same. That is, if you were able to trap all those stray gases and measure them. Which leads us to Section 4, Reactions in Action, Tracking the Suspects. Let's frame chemical reactions as the scene of the crime, where we have to track our atomic suspects as they interact and, frankly, try to disguise themselves. This timeline brilliantly illustrates a chemical process. Before the interaction, you measure the properties of your original substances, your suspects. During the chemical process, the actual reaction occurs. The original bonds break and the atoms regroup. Then, after the interaction, you have an entirely new substance. But remember our golden rule. Even though the properties are totally new, if you put it on a scale, it would have the exact same total mass as what you started with. The atoms just put on a new disguise. But how do you know for sure that a reaction actually happened, especially if we aren't balancing complex symbolic equations yet? Well, you simply track characteristic properties. If the atoms actually regrouped into a new substance, these specific properties are going to change. Is the density different? Did the melting or boiling point shift? Did its solubility change? Like, actually, maybe it used to dissolve in water and now it doesn't at all. Is it suddenly flammable? Does it have a completely new odor? If you see changes in these properties, boom, you have caught a chemical reaction red-handed. Let's look at some concrete examples from your unit to make this real. Say you take sugar and burn it. It turns into a black, sticky mess and lets off gas. It looks like the sugar vanished, right? But the smoke, the gas, and the black carbon ash left behind hold the exact same number of original atoms. The same goes for burning steel wool or mixing zinc with hydrogen chloride. You see bubbling, you see color changes, maybe you smell something new. That is the physical proof that the original atoms are pulling apart and clicking together in brand new formations. And finally, Section 5, your engineering challenge, controlling the transfer. Now we transition to the final application task, where you get to put these microscopic rules to the test in a real-world design project. Let's see how this builds into an iterative engineering design cycle. You are going to build a device that controls thermal energy using a chemical process. Step 1 is constructing the device itself. Step 2 is testing it by measuring the amount of substance, the time it takes, and the temperature changes. And Step 3 is absolutely crucial. You have to modify and redesign your device to optimize how well it transfers that thermal energy. You'll keep tweaking the design based on your data to make it better and better. To make your device work, you will explicitly use chemical examples from this lesson. Some reactions store energy, and some release it. For instance, when you dissolve calcium chloride, the atoms regroup in a way that actually releases thermal energy, which heats things up. Conversely, if you dissolve ammonium chloride, the reaction absorbs energy from the surrounding environment, which actually makes things feel cold. You'll be using these exact chemicals to optimize your device's ability to either heat something up or cool something down on demand. So, I'm going to leave you with this final, slightly provocative thought before you start your hands-on engineering challenge. We know the law of conservation of matter says the mass of your chemicals will never change during your test. The atoms just rearrange. But if the mass stays exactly the same, exactly how is that thermal energy, that intense heat or sudden cold, being transferred into or out of your device? Think about how the energy is hiding in the bonds of those unobservable molecules. Good luck solving the rest of the mystery in your project, and thanks for joining me on this explainer.